Was this back here? Minus e. Okay, so we had a question on this one here. There's several different ways that you can do this one. One way to do it is to a UDU substitution doesn't work because we don't have an e to the x in the numerator. So one way to get an e to the x in the numerator is to multiply top and bottom of this fraction by e to the negative x. Because e to the negative x times e to the x is going to give us 1. So that's one way to do this. Rewrite this integral. Like that. And then I get an e to the negative x on top. And on the bottom, when you distribute this through here, you get e to the negative x minus 1. And now we have a u du integral. Take u to be the entire denominator, and then du is the top part. Now we take u to be e to the minus x minus 1, and du is a minus e to the minus x dx. So I get a minus du times 1 over u. And that's just a logarithm. And u is e to the minus x minus 1. Another way to do it is with a double substitution. So another way start out with u being the entire denominator, 1 minus e to the x, and then du is minus e to the x dx. And so du divided by minus e to the x is the dx. Where minus e to the x is the same as u minus 1. So this becomes du divided by u minus 1. And so when we put those in there, we would have 1 over u times du over u minus 1. Or you can write that as 1 over u times u minus 1 du. And now this is a partial fractions type integral. We find the two fractions that add together to give us this one. And then we can integrate the individual fractions. So by partial fractions, 1 over u minus 1 is a over u plus b over u minus 1. So I have 1 is equal to a times u minus 1 plus b times u. If u is 0, I get a is negative 1. If u is 1, I get b is positive 1. And so we're integrating negative 1 over u plus 1 over u minus 1. And then that would give us minus the natural log of u. But u was 1 minus e to the x plus the natural log of u minus 1. So u minus 1 is minus e to the x. And then there's more ways. I saw all kinds of ways to do this one. I learned a lot just by grading tests. That's very clever. But only one of you tried the bonus, or got the bonus all the way through. Let's do the bonus. Why didn't you try it? Should I put the bonus first then? You were just tired? You were just tired of it?
Well, I was like doing it, but I tried to put it in like terms of why, which I think was my first mistake.
That was your first mistake?
Incredibly hard from that point forward, and I was like, I think I messed up. And I was like, you know what, I'm just gonna turn it that way.
Because I thought we worked that one in class. So the problem was something like this. You were taking the graph of y is equal to 1 over 1 plus x to the 4th, taking the region underneath, or I don't know if this was a 1 or not. The 1, taking the region under that graph. Let's see, when x is 0, y is 1. And we want to take this infinite graph here, revolve it about the y-axis to generate a solid for x greater than 0. So if you just did a regular old dx integral, then you've got your partitioning element parallel to the axis of revolution, which gives us the method of shells. So by shells, the volume is equal to 2 pi integral of r times h, and in this case, dx. Where r is just the distance from the y-axis to the partitioning element. So that's just going to be x. H is the height, which is given by the function value. So we're integrating 2 pi x times 1 over 1 plus x to the 4th dx. And we're going for all positive values of x. And so if we write this as a proper integral with a limit as n goes to infinity, put that x on top and write the x to the 4th as an x squared squared. And put the x on top, get up there. Now tell me how to do that integral. U is x squared, du is the numerator, right? So if u is equal to x squared, du is a 2x dx. So I'm going to get a half out of this. So I'll just take half of the 2 pi and put a pi out here. And so we're integrating pi times the limit as n goes to infinity, 0 to n, 1 over 1 plus u squared du. That's an arctangent. It's the arctangent of u. So we have pi times the limit as n goes to infinity of the arctangent of u, where u was x squared. So it's the arctangent of x squared from 0 to n. The arctangent of 0 is 0. So all I need to do is take the limit as n goes to infinity of the arctangent of n squared. And it's pi halves. So we have pi times pi halves, or pi squared over 2 cubic units of volume. Right? So this one was almost a harder problem than that one. What else? Anything? Okay, where did we leave off? You know everything there is to know about sequences?
Yeah, I think that's right now.
And what makes a sequence converge? Have we done all that? Peek at your notes. Check my glasses. Mind you hide them for me. Let's see what's in your notes.
Starting the arithmetic in geometry.
Oh, we were starting series already. Hoorah. Okay. Okay, let's pick her up from there. Well, I'm really impressed at how well you guys integrate. So now let's quit integrating. Let's just do other stuff. So what we've done so far in chapter 8 is talked about sequences and that a sequence converges if it has a limit. We denote a sequence something like this, and that's just a list of numbers. Where this is a general formula that generates the sequence terms. And a sequence converges if it has a limit. So all you have to do is take the general term and take the limit as the counter, in this case, n goes to infinity. If you get a finite limit, then that sequence converges to that value, which means that when you look at terms, that's the first term, these are the ANs, these are the Ns, which are counting numbers. So when you go way out here to a very large N, the terms in here might be doing something. But once you get past this very large N, they're all hanging around that number L. A very small interval around that number L with epsilon. So if they all start doing the same thing after a while, then that's the limit of the sequence. For instance, the sequence converges to what?
1/4.
To 1/4. As the limit as n goes to infinity of n over 4n plus 2. If you do L'Hopital's rule, you just get the 1/4 right off the bat. What about the sequence 2 divided by 3 to the n, which is the sequence 2/3, 4/9, 8/27, 16/81. What do you think? What do you think you know about that sequence? Converges to 0 because I have 2/3 to the n, which gives me 2 to the n over 3 to the n. 2 to the n grows slower than 3 to the n. If the numerator grows slower than the denominator, then the limit's going to be 0. Right, 3 to the n grows faster than 2 to the n, so it's a bottom heavy kind of fraction. If my fraction in the parentheses is the other way around, then my sequence is going to diverge. Goes faster on the top than it does on the bottom. So we pretty much had our little tower of power to help us speed up L'Hopital's rule. our tower of power, looks something like this. On the bottom of the power are things that grow real slowly. And so one of the things that grows real slowly for us something as slow as molasses is something like the natural log of n. And almost as slow as molasses is the square root of n. And then maybe n to the first power is a little bit faster. N squared is faster. The bigger the power, the faster the growth. Right? I don't know, what grows faster? N squared or 2 to the n, which is faster? Two to the n grows faster because it doubles each time. 2 to the n does indeed grow faster. Let me see that. All right, so if I start putting powers up here, 2 to the n grows faster, but e to the n is a bigger base, so it grows faster. 10 to the n grows faster than that, but factorials grow faster than those. And n to the n grows faster than those. So if you have the faster growing thing on the bottom of your rational expression, the limit will go to 0. If you've got the faster thing on the top, the limit will go to infinity. If you're not sure, you can try to do L'Hopital's rule. Now, when we start adding terms together, then we form a series. A series is the sum of terms in a sequence. So, section 8.2. So now we use this sum notation to denote the sum of, and then we'll use a counter, either a K or an N. I've been using an N. You can start your counter anywhere. I could start my counter at 0. I can start it at 15. I can start it anywhere. If I say I'm starting my counter at N is 1, then my general term looks like AN. That means I'm adding A1 plus A2 plus A3 plus A4 forever and ever and ever and ever. So we can kind of picture an infinite series as being the sum of the lengths of the sticks above each counting number. So if this is N, and these are the ANs. So this is 1, 2, 3, 4. Suppose A1 is here. Then this length represents our first term. And if A2 is here, then we got that length. And if A3 might be here, we got that one. You take all of those sticks, the heights above each of the counting numbers, and stack them one on top of the other, all the way down here to infinity. If the length of that cumulative stick is finite, then the series converges to whatever that length is. But if that length of that stick keeps growing, or we've seen some that oscillated back and forth, then that series, or the length of the stick, tells us that the series diverges. Okay, so if we stack these lengths together, get a finite value, then the series converges to that length. But if that length becomes infinite, then the series diverges. It's not that easy to tell when we're going to get a series to converge or diverge as it was for a sequence. We're going to have to do more than take the limit. A couple of things that we do in this section is recognize two special types of sequences. Sequences that have a pattern of partial sums. If I add up the first three terms, I form the third partial sum. If I add up the first four terms, I've got the fourth partial sums. If I add up the first n terms, I've got the nth partial sum. If I generate a sequence of partial sums that converges with a series, then the series converges. So if we can form a sequence of partial sums Sn, then we can use this to determine if the series converges. Where Sn, S1 is just the sum of the first term. S2 is the sum of the first two terms. S3 is the sum of the first three terms. And so on, so that Sn is the sum oh, I shouldn't use the same as my counter. Let's change my counter to a K. And K is equal to 1 to n of a K. If this sequence of partial sums converges to a number L, then the series also converges to that number L. I don't know if we did this one. Did we do the fact that this series, 1 plus a half, plus 1/4, plus 1/8, plus 1/16, that series converges. Did we look at the partial sums of this? Well, let's do that. Let's look at the partial sums and see if I can generate a formula that gives me what the n partial sums add to. If I can get a formula in here that depends only on n, then I can take its limit and see if this thing has a limit. So let's look at the sequence of partial sums. So here's why. My first partial sum is just 1. My second partial sum is 1 plus a half, which is 3 halves. My third partial sum is 1 plus a half plus a fourth. So if I take my 3 halves and add 1/4, then I have 6/4 plus 1/4 is 7/4. My fourth partial sum looks like 1 plus a half plus a fourth plus 1/8. So if I take my 7/4 now and add an 8, I can think of 7/4 as 14/8 plus 1/8 is 15/8. What do you notice about the nearest integer to each of these partial sums? What's the nearest integer here? 2. 2. They're all getting closer to 2, right? In fact, I can think of this 3 as 2 minus a half. I can think of this 7/4 as 2 minus 1/4. I can think of this as 2 minus 1/8. So the fourth term has an 8 taken away from 2. The third term has a fourth taken away from 2. And the second term just has a half taken away from 2. What do you think it looks like in general? 2 minus what? This is 2 minus 1/2 cubed. This is 2 minus 1/2 squared. And this is 2 minus 1/2 to the first. So notice that the power over there is related to the subscript. It's 1 fewer. So I can say that the nth term looks like 2 minus 1/2 to the n minus 1. So I got a general formula for the nth partial sum, just kind of by dumb luck or smart luck. And so if I take the limit as n goes to infinity of that nth partial sum, I'm looking at the limit as n goes to infinity of that formula that I concocted. 2 minus 1/2 to the n minus 1. Is that limit obvious to you what it is? The only thing that depends on n is down there in the denominator. 2 to the n is going to keep growing. Even 2 to the n minus 1 keeps growing. So 1/2 to the n minus 1 behaves like 1/infinity after a while, which goes to 0. So this fraction here is going to 0, which makes our limit of my partial sums equal to 2. And so this theorem over here says that if the partial sums have a limit, then the series converges to an infinite sum, S, which is also 2. So our series converges to 2. Yeah. That's kind of hard to do. We got kind of lucky in this one. Let me show you some others. look at this series. So try to find the sequence of partial sums for the series. I'm going to use K as my counter. K is equal to 1 to infinity, 1 over K times K plus 1. Try to find the sequence of partial sums from that series and then use it to determine if this series converges. So let's look what the series looks like to begin with. If K starts at 1, then if I just start running some numbers here, my first term is 1 over 1 times 2. My next term is 1 over 2 times 3. And then 1 over 3 times 4. 1 over 4 times 5. And so on. 1/2 plus 1/6 plus 1/12 plus 1 over 20. And so on. So we can mess around like this and actually look at the partial sums and see if we can come up with a general formula. But I want to suggest another way, since we're well versed at breaking things up into its partial fractions. Let's take that one fraction, 1 over K times K plus 1, and find the two fractions that were added to get us that one. Do the partial fraction decomposition, and maybe that makes this part faster. So if I just cross multiply, I get 1 is equal to A times K plus 1 plus B times K. If K is equal to 0, then I get A is equal to 1. If K is equal to -1, then I get B is equal to -1. What you got? Which says that this series is equal to the sum from K is equal to 1 to infinity of 1 over K plus -1 over K plus 1, or I can write the minus sign there. So now let's look at the partial sums using that expression. So here, S1 is the first term, 1 over 1 minus 1 over 2. S2 are the first two terms, where this is one term. So when K is equal to 2, I get 1/2 minus 1/3. Agree? S3 is the sum of the first three terms. So here are the first two terms, 1 over 1 minus 1 over 2. plus 1 over 2 minus 1 over 3. And now I add the third term, which uses k is equal to 3. When k is 3, I have 1 over 3 minus 1 over 4. I only put the parentheses there so that you could see the individual terms. S4 would have 4 pairs in parentheses. But the parentheses aren't important for adding sake. What if those parentheses are gone? What are you noticing about these terms? They cancel out. I got a negative 1/2 then added to a half. I have a negative 1/3 added to 1/3. My next term is going to have a negative 1/4 added to 1/4. So my nth partial sum, if I generalize that, would look like this. It would have my 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 dot, 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 right? I'm going to add a whole bunch of terms in here. So my nth one would look like 1 over n minus 1 over n plus 1. The term right before that, when k is n minus 1, would look like 1 over n minus 1 minus 1 over n. So there's a whole bunch of terms in there that are the same as the neighboring term, but opposite in sign. So they add each other out. These two add each other out. These two add each other out. They'll do that all the way down here. There's going to be something that adds to that and something that adds to that. This is an example of a sum that is said to be telescoping. All of the middle terms add each other out, and so this sum just collapses to 2 terms. This one and that one. And that's our general formula now for Sn. Sn is going to have that first term, 1, and the last term. No plus dot, dot, dots in the middle, they all add each other out. If we can get a general formula for the nth partial sum, then we quickly take the limit. And what's the value of that limit? It's 1. So the sequence of partial sums converge to 1. And so the series will converge to 1. So if by chance you can write your sequence of partial sums or your general term into something that telescopes, where you just have the first and the last, or maybe the second and the last, or the first and the second and the last, depending on how it telescopes. You'll see a few examples in your web work. If you can get a general formula for the nth partial sum, just in terms of n, and then take its limit, the series does what the partial sums do. If the partial sums get infinite, then the series diverges, has no finite sum. Okay? One example of a series that has a general pattern is a geometric series. It's not telescoping, but it's going to have a pattern where I can tell if a geometric series is going to converge or not just by looking at one of its features. A geometric series is a series obtained by taking the previous term and multiplying it by a fixed number to get to the next term. Geometric series has the form we have a first term, I'll call it A, I won't subscript it. Then I add to it A times R. Then I add a multiple of R to that, so A times R squared plus A times R cubed, and so on. R is the multiplier, it's called the common ratio. It's called the common ratio because we can find it just by dividing adjacent terms. I can divide the third term by the second term, and that tells me what my multiplier is. And it's the same as if I divided the second term by the first term. The ratio of any two adjacent terms gives you this multiplier. So here are some geometric series. What's my multiplier here? Yeah, to get to the next term, I always multiply by pi. The series that we started with, 1 plus a half plus a fourth plus an eighth plus 1/16. That was an example of a geometric series. What's our multiplier here? 1/2? Here's another one. That's a geometric series. What's my multiplier here? R is a -1/3. We can show in 3 minutes or less that the size of R tells us whether or not the geometric series is going to converge. And here's how. Let me take this and stop it at the nth term. So here, Sn looks like A plus AR plus AR squared plus AR to the n-1. The term number has a multiplier that's one fewer than the subscript. Now I'm going to create a new sum by taking that line and multiplying every term by R. I'm going to call my new sum R times Sn. So if I multiply this term by R, I'm going to get that one. So I'm going to line it up over here. If I multiply that by R, I get that one. There's going to be a term that looks like that one. I'm also going to get one more. Now I'm going to subtract the second line from the line above it. And so I get Sn minus R times Sn. And I chose to subtract because when I subtract, those terms that look alike will all zero out. And we'll be left with A minus AR to the N. I'm going to factor out Sn because that's what I'm trying to find, a formula for the nth partial sum. If I factor out the Sn, I'm going to have a 1 minus R right here. I'm going to factor out the A there, and I'm going to have 1 minus R to the N. And so I get my formula for the nth partial sum of any geometric series to be A times 1 minus R to the N all over 1 minus R. That's the sum of the first n terms in any geometric series. Now I'm going to take the limit as n goes to infinity. So in order for the limit as n goes to infinity of Sn to be finite, we need this stuff on the right-hand side to have a finite limit. But there's only one term that depends on n. These are all constants. Only this term depends on n. What size does R need to be so that R to the n doesn't go to infinity?
Less than 1.
It has to be less than 1. If it's a fraction smaller than 1, it's going to eventually go to 0. If that fraction is bigger than 1, it's going to keep growing. So this will be finite if R is smaller than 1. R could be a negative number. We need an absolute value to be smaller than 1. And if R is smaller than 1, then R to the n is going to go to 0. If that goes to 0, then this what's left is the sum of any convergent geometric series. This geometric series diverges because my multiplier is bigger than R. This geometric series converges because my multiplier is smaller than 1. And it converges to A, which is the first term, over 1 minus R equals A over 1 minus R. That's what we got a few minutes ago when we did the telescoping series for the sum of partial, the sequence of partial sums. This one's going to converge. My multiplier is smaller than 1, so it converges to A over 1 minus R. So 3 over 4/3, which is 9/4. If you recognize you have a geometric series, it's easy schmeezy to find whether it converges or not. And the added benefit is we can actually find what it converges to. That's the end of easy. From here on out, it's not. Thank you for hanging around a few extra minutes. Any questions, anybody? All right, we'll pick it up from here on Friday. Folks have any questions? Nobody's there. They left me.